Hello everyone and welcome back to the channel. Today we're going to be doing a forward pass and back propagation of a two-layer sigmoid activated neural network. That's right, our learning is going to get deep today. So we're going to begin over here with the forward pass. The forward pass is pretty straightforward. We're just going to begin by setting some bases right here. So let's first wrap in the biases with the weights and a 1 with this x input vector. And to be clear, when you wrap weights and biases together, what you're really doing is you're basically taking this matrix and you're expanding it and you're grabbing these elements and you're sticking them right there on the end. And then you can call it the wrapped matrix. If that makes sense, right? This is the split. This is the clear split between the two, but they're together and they're easier to manage. Okay, so let me erase this. Now the first thing we're going to do is we're going to wrap them together, and you remember you need to add a 1. You need to wrap a 1 to the bottom of the x because otherwise the dimensions will not match, and we're going to multiply them together here. And this multiplication is pretty straightforward. What we're going to do here is we're just going to write out what's happening exactly. So right here you just take the weights and the biases and you multiply them by x with the 1. Okay, this is what's happening right here. And this is going to get you a matrix that looks sort of like this. No, it's going to look exactly like this. We're about precision here. So it's going to be 18, negative 11, and negative 13. Okay, so this is the first multiplication. After this, you're going to want to activate this matrix using the sigmoid activation function. Now, let's talk about sigmoid. So the sigmoid activation function is a sigmoid of x equals 1 over 1 plus e to the negative x. That's sigmoid. And just for later, because we're going to need it, let's specify the derivative of the sigmoid. It's the sigmoid of x times 1 minus the sigmoid of x. There you go. No difficult derivatives required. Now let's get back to the forward pass. So we're going to just apply this classic function to this matrix, and we're going to get some values that are very close to 1 and very close to 0. So let's go ahead and just round those values down. Right? If you get something that's exponentially low, you get something really small, you could just round it to 0, get a 0.999, round it to 1. But at the end of the day, you're going to get a matrix that looks like this, 1, 0, 0. That's the output, and that's the first layer. This is the first layer right here. I'm going to move this down to give myself more space. And to go through the second layer, all we need to do is introduce the second set of weights and biases. So here we have the second set of weights, the second set of biases, and we're going to multiply this wrapped matrix with the output. And here's something to note. I'm just going to put a little bit of an asterisk. I'm going to put some dots right here and add a 1. Okay, because remember, if you wrap biases in, you need to make sure the bounds are compatible. Otherwise, you will get an error from your calculator and you will feel lost. But we're not lost here. We are found, and we will find that this multiplication, which I will specify here as the second weight, second bias, wrapped, multiplied, and let's give this a name. So right here we have x right here. So, we're pretty straightforward. On the YouTube channel, we're going to name this x2. Okay, this is classic. This is the out. By the way, this is the output. If I didn't specify already, this is the output, and we wrapped it with the 1. What are we going to get? Well, if we do the math, if you do the math, type it up on your TI something something, you're going to get a 1, 4 as the final, as the multiplication. And then let's just, this is par for the course. We're just going to apply a sigmoid activation function to each of these, and we're going to get 0.73 and 0.98. That's your forward pass. Done like dinner. Delicious. Well, now we have to go backwards through the network for the back propagation. So this is the juicy part. I'm going to just expand my canvas right here, and I'm going to move this down, move this towards the middle, because this is the focus now. We don't need to know our inputs anymore. I'm going to move this down a little bit. So we're done with the forward pass. Now we want to go ahead and go backwards through the network. Okay, where do you start? You have many options. Just kidding. You have one option, and that's to go right backwards through your sigmoid activation function. Okay, so you're going backwards through your sigmoid, and essentially, what's the derivative of the sigmoid? Okay, well, it's this right here. Let's just use this and apply this function to each of the elements in the output. Okay, so let's draw an arrow right here. Actually, let's not even draw an arrow. Let's just draw it right here. We're going to have the gradient. We're going to keep track of the gradient. And let's name these. We always want to name our elements because it makes them feel good about themselves. Anthropomorphize them. Just kidding, it's to keep track of them. So we're going to have here the second sigmoid, the gradient, and let's do 0.73 times 1 minus 0.73 and 0.98 times 1 minus 0.98. Okay, this is going to get us a final resulting gradient of 0.19 and 0.02 so far. Okay, so far so good. This is pretty straightforward. Now for the meat, for the meat of the back propagation. This is our multiplication of the two vectors. Now, I'm going to write a couple things down here, but do not worry. I'm going to explain exactly what's going on. So let's begin by writing the equation. What is going to be the gradient of the second weight and second bias wrapped? Okay, it's going to be the second sigmoid gradient multiplied by x21 transpose. Whoa, that is daunting. And I'm going to write the other one here. This is going to be the gradient of x2, and this is going to be the second weight, second bias, transpose multiplied by the second sigmoid. All right, let's go. I'm going to go on a side tangent, a very related side tangent actually to this topic. Let's talk about partial derivatives. The derivative of x squared with respect to x, of course, is 2x. Okay? The derivative of x squared, this is basic calc. The derivative of 2x is 2 with respect to x, of course. Now, quiz question, what is the derivative of xy with respect to x? Well, it's y right here. Let's do a little bit of an expansion. We'll put x on top and y on the bottom. What are we doing here? What's going on they come together multiplied. Okay, xy. Wait a second. You go backwards. If we do xy here and take the derivative with respect to x, we get y. And if we do xy here and take the derivative with respect to y, we get x. But let's not forget a very important two bits of information. This is 1 times y and x times 1. Oh man, this rules. This looks exactly like these two equations right here, where you replace the current element with the partial of the sigmoid, right? Of the gradient of the sigmoid. Note that order matters because it is matrix multiplication. This is why you have this sort of exchange, right? Where you're multiplying the output concatenated with the 1 transposed by the gradient here, and the weights and biases concatenated transposed by the gradient here. And remember, you're transposing the other, right? The weights and biases here, or the second input here, which is just the output of the first network. You're doing this because you need to match the dimensions. The dimensions need to match with the matrices. Okay, so now that I've gotten that out of the way, the actual matrix multiplication is not rocket science at all. I'm just going to move these out while we do these computations. So let's go ahead and plug it into the calculator, and we're going to get something that looks like this. For this, we're going to get 0.19, 2 zeros, and a 0.19. And you're going to tell me, man, this looks a little bit suspicious. Why do you have a 0.19 again, a 0.02 again? Well, this isn't actually the gradient for just the second weight. This is both the gradients for the weight and the bias. Okay, let's note specifically where these are. Okay, so right here we have the gradient for the weight 2 and the bias 2. Okay, that looks a lot better. That makes a lot more sense, right? Let's do the same thing down here. Do the same thing down here to get a beautiful matrix that looks something like this. Negative 0.32, negative 0.55, negative 0.15. It looks like I ran out of space. Got to erase this real quick. And finally, a 0.59. And again, you can see that you can split it right here to get the gradient with respect to x2 up here, and the gradient with respect to the 1 down here. All right, well, we're done with half, which is of the back propagation, which is pretty good in my book. Pretty good in my book. I'm going to move this over to give us a little bit more space, just so we can work. We don't have to work cramped right here, you know what I mean? Okay. Okay, let's go and do the first part as well. Right here, we're going to use this output, and you're going to see something quite interesting come up. Well, what's that? What is that? And we're going to just go ahead and apply the derivative, and we're going to go 1 times 1 minus 1, and then 0 times 1 minus 0, and 0 times 1 minus 0. Wait, what? What the heck? Oh, look at that. It's just a vector 0. making your life a whole lot easier. But this is fine. This is totally normal. And what you will note is that when you continue backwards, everything is going to line up and just come out to a bunch of vector zeros of the appropriate size, right? And you can tack on or off this 1 down here, but even if you do, it's just 0 as well down here. Just depends on compatibility of size. Now, I will rewrite these equations here just to make it clear what's going on. Bias 1 equals, and then it's going to be, and then this is going to be, we're going to name this the sigmoid 1 gradient. Look at that. It's the sigmoid 1 gradient multiplied by x concatenated with 1 transpose. What you're going to actually just end up with is a huge matrix of zeros. 1, 0, 2, 0, 3, 0, 4, 0, 4 zeros in the middle row, 4 zeros on the bottom row. And if you wish to know, which you should wish to know, this is the split right here between the 1 and bias 1. And then if we come down here, we're going to find that the gradient of x1, 1, which is not just x, we're going to get the weight, the first weight, first bias transposed multiplied by the sigmoid 1 gradient, which is just going to get 0, 0, 0. So many zeros. This just makes your life easier, honestly. Fewer calculator computations. You just have to match up the correct bounds. All right, so let me scroll properly here. This is the full forward pass and back propagation of this network. You're done. This is it, right? And if you care to specifically know, you'll probably want to focus if the question's asking you to, go downwards along the gradient. You're going to want to use this right here. Maybe you want the bias, but it's mostly this one and this one, because these are the values that have to do with the weights, because you can update the weights. You can also update the biases right here. I hope that made a whole lot of sense, including why you are multiplying, right, these gradients in this specific order. Now, remember, order matters. Do not mess with the order, or you will be served. All right? You'll be cooked. But you won't be, because you just learned how to backpropagate through a 2-layer neural network. Now, what happens if it's a ReLU? That's the big question that everyone's asking. What happens if your activation function, instead of being sigmoid, is ReLU, where you take the maximum between, you just cut out negative values. You have 0 and 1. Well, in that case, you're going to have to multiply, essentially, your gradient with a matrix full of 1s and 0s, depending on whether the value is negative or positive. And you don't even have to do fancy math, because you could just go in and say, example, I'm going to use this different color for the example right here. This blue, this gray. lavender. I'm going to say that, maybe you have something that looks like 0.9 and negative 0.1, right? If you have an ReLU, you'll find that it comes out to 0.9 and 0, right? Not bad at all, period. So this is it. I hope you enjoy the tutorial. Remember, when you put your mind to it, the concept is right in front of you, right? Remember to practice for any upcoming exams you may or may not have. And comment down below if you've got any questions about anything I talked about in this video. Have a fantastic day. And remember, back propagation is the best.